Hello everyone, and welcome to this tutorial. Today we'll be examining this case study, the surface modeling of a handheld beauty device later on. I'll also show you a few similar beauty products and walk you through a comparative analysis. In our previous session, what did we cover? We covered using multi-rail sweep and loft to construct a continuous surface. This involved managing curvature, continuity, and rational section fitting. Different product forms have different requirements. For instance, our device here has a fully contoured body, but in this area of the form, we also have these tapered or chamfered features. These are the chamfered surfaces. I won't delve too deeply into these here. Their purpose is simply to enhance the product's overall feel and quality. The primary form requirement is this base surface, which has a smooth pebble-like shape. In fact, this type of organic form is very common in industrial design, especially for consumer products like this. It provides the user with a sense of rounded, comfortable solidity. Alright, let's look at the surface. Last time, we discussed that golden surfaces are quite effective for fitting single-span surfaces. However, that doesn't mean they are completely incapable of creating complete, complex surfaces, right? So today, we'll use this style mesh surface tool to demonstrate how to use a mesh surface to construct a complete large surface based on a curve framework. First, let's examine this main surface. From the top view, you can see its profile is like a racetrack shape, which then blends down to form this 3D surface. In the last episode, I introduced these methods under curved shapes, the first one being called curve array. While it can achieve a similar outcome based on a profile and guiding rails to form a closed surface, the result is often less than ideal. Its underlying algorithm isn't the best. Therefore, the kernel workbench tool that performs network skinning, the network-based mesh skinning, produces a visibly superior result. Let's first check its information. Look at its surface structure. It has C2 continuity, 500 control points, degree 3 in both U and V directions. Let's observe the grid lines. Their direction, you see. Look at the flow of these UV lines. Their distribution is very uniform. However, using the curved shapes tool, it cannot fit a surface to achieve this quality. This is because both curve array and multi-rail sweep are rational methods. They are profile-based. They are rational nerves, but when fitting to the end points, it should fit to n data points, not n profile curves, hence the suboptimal result. Let's look here at the basic setup of this golden surface. We'll switch to the wireframe view. In the wireframe view, you can see we have constructed the first guide rail here and the second guide rail here. These represent the two primary rails defining the U and V directions. They are the rails that control the surface curvature. Then, the profile shape at the top is used to generate a surface that fits these rails. The fitted result is what we see now. Therefore, in different scenarios, different interface tools have their specific applications. As we've covered in previous tutorials, let's first examine a few other products. This one, for example, is also a facial device design. Notice that this surface is also composed of separate parts. This is the primary surface. This is the B surface. Surfaces are not fully continuous. They are disconnected here. The second surface is also separate. With this form, there is also a break at this location. This is another major surface, also disconnected. This product is similar. This surface is also separate. Even though the surface curvature changes dramatically here, this area is actually a distinct surface. Here, the designer used a clever technique on this part of the surface. An extrusion was added. This extrusion serves two purposes. First, it creates a transitional effect between these two surfaces, making the visual shift much smoother. However, the original surfaces, if you disregard this extrusion, are still separate. They meet at an edge for such adjacent surfaces. The common design solutions are either to add a decorative strip between them, which facilitates the transition. This serves a decorative function while also acting as a visual bridge. It helps the two surfaces transition more naturally. Alternatively, you can use a rounded fillet to make the product's form flow more naturally. This product is an example of what I just described. Between the primary surface and the front B surface, there is a decorative strip. This appears to be a chrome decorative strip. Its role is to transition between the two surfaces visually. This method ensures that during transitions, the product looks more natural. It serves as a connecting bridge, depending on different styling requirements. We choose different transition tools, for instance, a single unified surface, like the one from our previous case study, and also shapes like this one. Shapes like this are also created by joining together two distinct primary surfaces. When we need to join such surfaces, we either apply a fillet to the sharp peak to soften it, or we add a decorative strip. This strip follows the surface's flow lines to provide a transition. Another option is to create a simple extrusion, a straight stretch, which also serves as a transition. Let's return to our case study. We'll start a new document. The front end is a rounded rectangle. We'll draw another one. Let's create a rounded rectangle on the XY sketch plane. Once created, we switch to the generative shape design workbench. We need to segment all four boundary curves. To do this, we first need to create cross-section curves in the U and the directions. Now, with our boundary curves segmented, we can proceed. Next, we create a line here. Then switch to the part design workbench. We'll extrude this line using the current sketch plane as reference. This projects our construction points. After projecting them, we draw a spline. We have the two lines from section 4.3. Now, in the other direction, we'll also create a straight line. We'll extrude this line as well. Use this extruded plane as a reference. Similarly, derive 2 points from it. Then draw a curve like this as well. Ideally, these two curves should visually intersect. Alright, after completing all these steps, we'll join together all the curves we previously split. Once the join is complete, we select all these curves and create a mesh surface. At this point, we obtain the desired result, a complete large surface. If you are not satisfied with the result, you can still make adjustments. For instance, here, we could make the outer contour of this area larger. That is perfectly fine. Now, let's look at it in shaded mode. It remains very smooth here. Take this transition area, for example. Since this section is a straight line, when it curves down, it creates this kind of light and shadow transition. During our zebra stripe analysis, this area actually shows very smooth continuity. So this is the method we use to create such large surfaces. Whether the base shape is a racetrack, a circle, or an ellipse, the method is the same, including the surface on our model here. It is actually created the same way, composed of several curves. Starting with an ellipse, we connect a curve here. This connecting curve maintains G3 continuity. Then, using curves along the U and V directions, we control the surface's formation and the curvature variation during the process to obtain our desired surface. This block surface features a completely smooth transition. This also applies to surfaces like this one, which is a single span surface. The seam in the middle is purely a stylistic requirement. For stylistic purposes, we can use certain techniques to make its surface transition by adding decorative strips or using rounding techniques. Imperfections become invisible to the naked eye. This approach actually forms a foundational modeling step for us. Later on, we will actually need to perform some additional detailing, like adding chamfers or creating separate surface layers. These are decorative and styling modifications. Here is what is important to note when blending such irregular surfaces together, especially here where we have a racetrack shape above another distinct shape below. During the blend, we should try our best not to alter its weight points. Do not change the weight settings for curvature within the sketch. Keep them at their default values. The curves should also ideally be cubic splines, specifically of degree 3. You could create curves with a very high number of points, high degree curves, and then use the control points. to adjust the curvature. However, this is generally not recommended because it can cause significant deformation and make the surface prone to unsmoothness. For example, if we change its weight value here, say by setting this global factor to 3 to make them equal, let's take another look. Now we can see that compared to the previous surface, the convergence here, the degree of convergence in this area is noticeably higher. This area shows significantly more convergence than before. During a curvature cone analysis, when we drag this line here, although it maintains a certain degree of continuity, the transition in this region is actually not very smooth. This is especially true when the weight point is changed significantly. For instance, if we change this value to 10. Now, after adjusting the weights, let's take a look. Compared to the previous surface, haven't a lot of sharp edges appeared here. The zebra stripe patterns in these areas here don't look good at all. In fact, they look quite poor. Especially here you can see a lot of jaggies, many jagged artifacts. Even this area has a lot of jaggies. These jaggies indicate that our surface is actually not smooth. So this is a key point to note. Look at this area of ours. Before we changed its weight, the surface fitting process had very smooth transitions. So as you can see, it is best to keep these splines as 4th or 5th degree curves if possible, and avoid modifying the weights on the curves as much as you can, because it is not like the multi-rail sweep in our curve tools, which calculates based on freeform sections. Our mesh surface tool, when it skins a surface, doesn't use that kind of freeform computation. Take this surface, for example. It is the same masonry. The transition between this surface and this one is also very smooth. It doesn't make the curvature so unpredictable. Therefore, the surface it generates is perfectly fine. Alright, that wraps up all the content for this video. If you found this tutorial helpful, please remember to like, share, and subscribe.